Hello, welcome to another edition of Bed Talks. Today, what we're going to tackle is Chapter 13. Chapter 13 in Calc 3 is all about vector valued functions. And what we're going to be doing here, we're going to be tackling this as a review of what we tackled before we just left for the virus outbreak. And so we're going to just discuss kind of the overview, the big things, the big concepts that we're going to need going forward for vector valued functions. So in this case, let's first talk about, I guess, more specifically, what is a vector valued function? A vector valued function is some function like r of t, and it has 2 or 3 components. But what this basically is it tells you that if I plug in a time, what point am I at? And kind of thinking about the general trajectory of a vector valued function, it constructs a space curve. So if I have something like this, right, this might be r of t. And what it's basically doing is that every single time I plug in, it's only one parameter here. And what it basically happens is I plug in, maybe this is at r of 1, maybe this is at r of 2, and so on. Maybe this is at r of 3. And slowly but surely, if we plot all these points, we get these vectors that kind of just plot all the way around, and we get the space curve. And this kind of talks about the trajectory of a point or a particle in space, just in general. If I have one parameter, if I parameterize something and I have one parameter, that is going to represent a line or a curve in space. That's what's going to happen there. So what are the things we can do with this? Well, many times it's going to be kind of difficult to try to figure out maybe the domain of a function, maybe where it goes, how does it look? That's kind of the first thing we think about. And as a reminder of how we calculate the domain of a function like this, if I want to calculate the domain of r of t, I calculate the domain of each of the individual functions. So for instance, if this was like the natural log of t, t and I don't know, t squared over 2, we see here, for instance, that the y and the z components are always continuous for all t, but the natural log of t is only defined when t is greater than strictly 0. And because of that, the domain of this entire function is t greater than 0. So we could write something like 0 to infinity. If it was something more complicated, we would have to take into consideration all 3 of the domains and then kind of think about the intersection between them. This gives us the ideas of where my particle is lying. Where is it moving? What time is it moving at? We usually think about this in time. And r of t can be thought about as position, and we'll kind of get to that going forward. Now, the next thing we usually like to do is think about, okay, what do these things look like? Right? What do these things look like just in general? So let's even take this one for example. Let's say I give you r of t here, something like this. Right? What does this look like? It's actually very difficult to think about what this looks like. And it's not too easy to think about at all. And so what we like to do is we have a couple of different techniques. The biggest technique I would like to think about here, and one that's really, really important to at least start to visualize these things, is the idea of projections. And the idea of projections is as follows. So we have a couple of ways that, in a 3-dimensional sense, how does a vector field move, right? How does a vector move, right? So we have a couple different directions that I'm kind of thinking about as a cinematographer. I can either look at it from, looking at the XY plane, looking straight down and looking at the XY plane, looking at the XZ plane, and looking at the YZ plane. I have these different ways, and by looking at it in different ways, I can actually see maybe what imprint, if I project that curve onto these planes, these 3 planes, what is it going to look like? And kind of using these 3 planes to reconstruct, what actually it is, it's actually really important. And it kind of gives us maybe some insight as to what the curve actually looks like. So that's the first thing, so the idea of projections. So let me just write this curve up here again, just so we have this. So I have the natural log of t, t, and t squared over 2. So this basically says that x moves as the natural log of t, y moves as t, and z moves as t squared over 2. Now, some of these are going to be a little bit tough to draw, but we can at least gain some insight. I've written out my parametric equations here. So if I project this onto the xy plane, this is only when I have x is equal to the natural log of t, and when y is equal to t. Now, what does this look like? The problem that usually we come from here is it it's very tough to see, right? If I have time t. T is just very tough for us to visually think about. We usually like to think of things in x, y, and z. It's a little bit easier for us to draw out, right? So what I can think about is, okay, I have y is equal to t here. I have x equals the natural log of t. So why don't I just replace t with y? Because y is equal to t. So this can then come back to x is equal to the natural log of y. That's pretty nice. And what I could do there, if I actually exponentiate both sides, I can actually solve for y. And I can get that this is y is equal to e to the x. So what does that look like? On my xy plane, I know what y e to the x looks like. Looks just like that guy. And that's the projection. And I want to be actually very careful because as y increases, as t increases, y is going to increase. So the curve is actually going in this direction. You can kind of see which is going. So if I look at it from this way, all I'm seeing is I'm seeing this kind of exponential kind of go. That's pretty cool. Okay, so that's the xy plane. Now let's see what happens with maybe much like the xz plane. Particularly the xz plane. Again, I have x is equal to the natural log of t, and z is equal to t squared over 2. Now this is a little bit more complicated, right? It's a little bit more complicated. It's not as easy as just me plugging in there. But we can at least get maybe some ideas here, maybe in some form. Now, the best way I would start to think about it here, you can again try to solve for t if you want. So I can get this as 2z is equal to t squared, and then square root both sides. I get t is equal to the square root of 2z. Now, I would have to kind of put a plus or a minus out here, which becomes a little bit of an issue. But I wanted to show you something. I can't have a minus in here, right? If I plug in now t for this, I can't plug in a minus. So I'm only going to plug in a plus. I'm only going to positive amount. Because also, I know z is always a positive value too. It's always an important thing to realize. So because of this, I'm going to plug in just the positive root, and I get that x is equal to the natural log of the square root of 2z. Again, exponentiating on both sides, I can get e to the x is equal to the square root of 2z. But now I have stuff in z's and x's, which is a lot better for me. I square both sides, I get e to the 2x is equal to 2z. And lastly, I get z is equal to 1/2 e to the 2x. Okay, so it kind of looks in the same exact way as the last one did, right? But again, we have another exponential like that. Maybe a little bit of a faster decay, actually a faster decay, faster growth here. But we start at 1/2 because of this 1/2 here. And again, as t increases, z is going to increase. So this is the zx. And we're again going in this direction here. And you can do this with the other one too, and you can gain at least some good insight. So this means that if I'm looking at it from this way, I'm looking at it like an e to the x. You kind of see this, like the yz plane. I'm going to kind of probably have a parabolic aspect. If I plugged in y here, I would get z is equal to y squared over 2. So it kind of look like, just as a quick side note, it kind of look like that. So this is the only one that's a little bit funky because the other two are pretty clear exponentials. So this guy is the idea of projections. And this idea of projections is going to come in handy as we go forward. We can also think about asymptotic behavior. So as time goes to infinity, right, x, y, and z will all go to infinity. As time gets closer to 0, this gets to negative infinity, this goes to 0 and 0. So if I start to add all these things up, we might be able to gain some insight as to what the kind of curve looks like. Okay, now with that in mind, we can start to think about, okay, well, what can I do with these vector value functions? Can I integrate them? Can I differentiate them? And yeah, we can, exactly as you want to. So let's just, again, have a very general f of t, g of t, and h of t. If I want to integrate r of t here, I can go ahead and integrate each one of these individually. dt, integrate g of t dt, and the integral of h of t dt. Now, I want you to be very careful, though, because when we integrate, we always get a constant of variation. So, for instance, if I had something like this, just to kind of, the derivative, right? The derivative is going to be r of t. But Now, in the same exact way, I would get a constant of integration. I would get a plus C1 here, I would get a plus C2 here, and I would get a plus C3 here because of a constant of integration. So if I have all three of these C's, I'm going to get a vector of integration if I pull this out. So many times you have to just be aware that I have to, in many cases, solve for this solve for this C, this integral coefficient here, this constant here. It's pretty important to do so. So if I'm able to do that, right? If I'm able to do that and solve for C maybe with some initial condition, like what's happening at 0, what's happening at 1, something like that, I actually get the full, I can recover the full equation. Again, if I want to differentiate, you do it as well in the same exact way, right? I just take the derivative of all of the insides there, stuff like that. Yeah, so that's kind of the idea. Now, a couple of other important facts that we might want to know. The first thing that we want to try to think about is arc length. Now, if I tell you I have an arc, let's say I do have this R of t here. Now, what can I tell you about this? Well, what we're going to say is arc length is arc length. And the arc length, let's say I want to find this from A to B, for instance, the arc length from A to B. So kind of going forward, if I have something like, something like this, and I want to find the arc length between here and here, it's not really obvious what to do. But we could find by using the same techniques that we did in Calc 1 for arc length, thinking about actually parametrizing a curve as we did back in Calc 1, we can just extend this very nicely. So L then could be calculated as the integral from A to B. Everything is summing all up, and summing all these different possibilities as. And what we're going to do is it's actually kind of the norm of the derivative. So something like f prime squared plus g prime squared plus h prime squared dt. If you note here, this kind of looks like the norm of that vector. So we can just instead write from A to B of the norm of r of t dt. And this is how we usually calculate arc length. What we do is we find the norm, the magnitude of the derivative, so it's related to the slope. You kind of imagine, so what I'm doing in the most basic sense is I'm kind of simplifying every single point. I have this derivative, I have this derivative, I have this derivative, I have this derivative, and I'm adding up, I think, like these polygons, kind of think about them as. And I'm getting them smaller and smaller and smaller and smaller, right? I'm summing. So I have an infinitesimal sum, and that's kind of why I have this integral here. So if I want to find arc length, that's kind of how I do it. Now, with this in mind, we have the idea of arc length. We can then start to think about some important vectors, that might be important for us going forward. One of them, we already have dealt with a lot. So, let me show you something here. One idea that you might want to have now, and this is where we're going to start to get into a little bit more about vectors, specifically of vector equations, is we have here, if I draw out a graph, I have this part right here, which is a tangent. Right? This is just a tangent curve here. Now, if I wanted to think about this, this is just r prime of t. However, I know r prime of t doesn't have to be a unit vector. I think we'd all agree on that. It doesn't have to be a unit vector. But if I wanted to find a unit vector that's tangent to the curve at a specific point, that's just called the unit tangent vector. Now, how do I create a unit vector? As we've kind of talked about before, to create a unit unit vector just in general, I divide it by the magnitude of that vector, of said vector. So if I have a, I just divide it by the magnitude of a. In this case, I know my unit tangent vector is going to be going in the direction of r prime of t. And so therefore, what I can do is I can just divide it by the magnitude of r prime of t. Now, I have the unit tangent vector. My goal now is to come up with two other vectors. I want to basically construct a new coordinate system. Maybe x, y, and z doesn't really work for me. Right? Maybe it's a lot better for me to think about the particle moving in a very, very interesting trajectory. And it's nice for me to kind of be a cinematographer again and kind of move with the particle. Maybe there's some more important vectors for me to consider, and to think about how the vector's moving, how is it manipulating, how is it going about doing that. And one other way to do that, maybe there's a nice way to think about this, is to think about this guy right here, which I will call the normal vector. I'll now call this the tangent vector. Now, the normal vector here at different points, normal vector, maybe stuff like that. The normal vector is always perpendicular to the curve. And it's always then perpendicular to the tangent vector. Now, how do I come up with that? How do I come up with a tangent vector? How do I come up with a vector that is perpendicular to the tangent vector? Well, it's a nice little trick to realize here. I hope we would agree that the magnitude of the tangent vector is 1. Yeah, and this can be written in the same exact way. So the squared is also 1. And so I hope you'd agree then the dot product, which is equal to the norm squared, a1 squared plus a2 squared plus a3 squared. If you're having trouble thinking about this, stop for a second and think about that. But the dot product is just equal to the magnitude of squared. So this has to equal 1. Let's take the derivative of both sides with respect to t. Now, if I want to take the derivative of a dot product, what I usually do is I kind of use product rule. So f dot g is f prime dot g plus f dot g prime. This side's going to be 0. So I'm going to get something like tangent prime of t dotted with the tangent vector plus the tangent vector dotted with the dot product of the derivative, and this is going to be equal 0. If you start to think about this, it's going to just be the same thing because the dot product is commutative. So here, I get this guy, 2 of them, the dot product of the tangent vector and its derivative is 0, and therefore I can get rid of this 2. I'm going to say the dot product between the tangent vector and the derivative of the tangent vector is 0. So what does that mean? The dot product of 2 things is 0. They have to be orthogonal. And so therefore, the derivative of the tangent vector is the direction of the normal vector. It's kind of cool. So that's why we can do that. And so therefore, the unit normal vector can then be written as the derivative of the tangent vector. You have to be careful because we want this to be a unit normal vector divided by the derivative of the tangent vector, like that, the magnitude. This is my unit normal vector. Unit normal tangent vector, unit normal vector. So now I have 2 vectors that are perpendicular to each other. I need a third. How do I come up with a third vector that's perpendicular to both of them? If I have 2 vectors and I want to find a vector perpendicular to both, I take the cross product. And so therefore, this is what's going to come the binormal vector. And the binormal vector here is the tangent crossed with the normal vector. So we have our TNB frame. And this TNB frame comes a lot from Einstein's relativity and thinking about spacecrafts and aerodynamics too. It's a really important idea of thinking about, in this case, if I use the right-hand rule, the TNB frame, B is going to be coming out. Okay. So if I want to find the TNB frame, I kind of go through this process here. And note here, just by the way, that if I have, because these two, the tangent and the normal vectors are unit vectors, I know the cross product will be a unit vector. You can prove that if you wanted to. So that's how you calculate the TNB frame. And the last thing I want to talk about, at least in this kind of part, is the idea of curvature, because that kind of gets to a really interesting point. So I think we would all agree, at least the last thing, at least kind of thinking about this, I think we would agree that, let me see if I have any nice things. Oh, I did, hold on. Great. So I'm going to use this again. It's a map charter. So I think we would all agree that this wire right here is pretty straight. So it has very little curvature. How about this wire? Right, this is pretty curvy. Now, why is that? Right? Why do we say this is more curvature? Why do we say that? Well, if I take a look at this, would you agree that the tangent vector, as I move along this line, is not going to change a lot? Right? The tangent vector is going to stay the same. But if I have something like this, right, as I move around this curve, the tangent vector is changing very, 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 very rapidly. So what I should think about is the idea of curvature comes from how fast does the tangent vector change as I move throughout my arc? If we think about it that way, well, this becomes a lot simpler. And we can actually write down a mathematical formula for it. I think I've lost my marker. Oh, there it is. I don't know what I'm doing. Got it. Okay. With this in mind, we now have the idea of curvature. So the idea of curvature, thinking about this, is how fast does the tangent vector move with respect to arc length? S is arc length here. That's just an important part to know. I didn't really talk about arc length too much, at least the arc length function. And how fast does it move, magnitude-wise? So if you'd agree, I think this part of the curve up here is very curvy, so it's a little bit more higher curvature. This part also has pretty high curvature. This part right here is pretty flat. So we expect this to have very, very low curvature because the tangent vector is not changing. We can replace this, and we can have a couple different formulas for this. We're not going to really need to know these formulas, but the main one is to realize that if I divide this side by dt and this by dt, this top part would just be the magnitude of the derivative of the tangent vector, and the bottom here, because ds dt, you use the fundamental theorem of calculus, right, and from my arc length formula to get this magnitude of r prime of t. And so doing this will now allow you to come up and construct, different ways to come up with the idea of curvature. And this idea is going to be pretty present in anything you do. And there's a lot of different ways you can calculate that. Lastly here, and the last thing I just want to talk about is acceleration, velocity, and all of this stuff. So we usually say r of t is position. Where is the position of the particle? Right? R of t is just moving all around somewhere. It's somewhere around the Earth, right? Just moving in this case. Where at every single time, what's my position? If I take the derivative of it, we usually denote this as a v of t because we usually call this as velocity vector. So the first derivative comes up with the velocity. And lastly, the second derivative, we call this as acceleration. How fast am I moving around the curve, basically? How much force is actually acting on it? It comes that way. Because force equals mass times acceleration. So acceleration kind of mimics force in some way. Another important thing to note, the magnitude of the velocity is equal to speed. As a reminder, velocity is kind of both the direction I'm going and how fast I'm going, and the speed is specifically how fast I'm going. It does not matter about direction. And we can calculate this in many different ways. So we have a couple different ways to calculate this. And if I have the acceleration, I can integrate up to get the velocity and so on. But as a reminder, whenever I integrate, I always have a constant of integration. So again, if I have something like, as a reminder, something like, if I have the acceleration here, I can even just do the velocity. We can even just do a simple problem. Remember, the velocity is equal to t natural, let's just do 1 over t, and, sine of t, something like that. And I told you that the initial position here, maybe at, pi, maybe a little bit better there. Initial position at pi is equal to 1, 0, 0, something like that. And I wanted to know, what's the original position? Right? What's the position vector? What's the how does that move? What I could do is I could integrate v of t. I know r of t, the position, is going to be just the integral of v of t. Integrating this, I would get t squared over 2. Integrating this guy, I would get the natural log of t. And integrating sine, I would get negative cosine. But I have to be careful that when I add, when I take an integral, I have to add this coefficient here, this constant of integration. In this case, it's a vector of integration, a constant vector of integration. To find this c, I use my initial condition. So I remember that r of pi, if I plug this in, is pi squared over 2. This guy would be just the natural log of pi, and this guy would just be negative 1. Actually, sorry, negative 1, because cosine of pi is -1, so this becomes just 1. And now plus this vector has to equal my initial position of 1, 0, 0. And what we could do then is we could see that the c here would then just be 1, 0, 0 minus this vector. So therefore, this just becomes 1 minus pi squared over 2. This just becomes the negative natural log of pi. And lastly, this just becomes -1 just by subtracting that over. And therefore, we can then plug this back in, and that's our official position vector. So this is kind of all the important stuff that we'll need, at least from these sections going forward, and kind of as a nice review. So just as a general idea, if you're having trouble visualizing vector valued functions, project the surfaces. That's going to be really important just in general. Projections are going to be super important as we go forward. So make sure you know how to project things and like setting things equal to 0 and all that. We also then tackled, integration and differentiation and the different types of vectors that we have. Arc length is going to be important. Arc length is going to be actually really, really important coming forward for some formulas in chapter 16. And lastly, how do we integrate? Making sure we have this concept of integration is always going to be an important thing going forward. And that's it. So this is chapter 13. And yeah, so tomorrow we start chapter 14.3 or 14.4, going forward from there, and we're going to go. So I hope you guys are doing well. And yeah, have a great day.